So, hi everyone, thanks for joining today. Today, my colleague and I will present on how finite element modeling in MIDAS FEA NX was used to inform the repair strategy of a half joint. But before we get into the technical content, let me quickly introduce ourselves. I'm Luke Fox. I'm a senior engineer based in the Manchester office. I have over 7 years experience and I am the UK MIDAS Champion. And joining me is my colleague, Rajesh N, who is based in Noida. He's a principal engineer with over 20 years of experience and is the MIDAS Champion for India. So before we dive in, I'd just like to do a health and safety moment. You may have seen a version of this stress performance curve before. There's a number of iterations out there that have recently been circulating. It essentially just shows how workload, which in turn can be stress, it can be related to performance. And I've kind of broken the graph up into 3 segments. The first is when work demand is low, which can lead to feeling unchallenged, feeling bored, so you can start to clock watch, can lead to procrastination, so a task that can take, or supposed to take a day, may take a week, and it can make your mood just feel flat, and overall you can just feel disengaged. We then have what I've defined as the optimal zone, where demand is balanced, and that's kind of when we tend to perform at our best. We feel motivated, engaged in the work that we are doing. It helps us stay focused. We tend to be more productive, and generally we'll feel more motivated and energized by the work that we're doing. Just, however, when the demand becomes too high or stays high for a prolonged period, it can lead to fatigue, which in turn can increase the likelihood of errors being made. It can make us feel overwhelmed, can make us feel drained, and in some cases can cause exhaustion and burnout, all of which can increase anxiousness. And I have seen too many instances where colleagues and friends are, feeling stressed and overwhelmed because they simply just have too much to juggle, and as a result, they become spread too thin, and then they kind of then start to tip into that overload zone on the graph. So if you do notice a colleague who seems under pressure, just reaching out and asking, "Are you okay?" can make a real difference. And if you don't feel comfortable doing that directly, speak to someone who is better placed to help. Remember, you don't always need to have the answers to the questions. It's simply listening can be enough. And if you're feeling overwhelmed yourself, just please reach out to someone. Don't suffer in silence. Just take the time to talk. It really can make the difference. So with regards to the agenda of the presentation, we'll start by giving a brief introduction to the structure and explaining why a repair strategy was needed. We'll then look at why conventional assessment methods weren't sufficient in this case and explain why 3D finite element modeling was chosen to better understand the behavior, particularly during the repair stage. We will then also briefly discuss the reasons for working within the MIDAS ecosystem, from creating and developing the global model in MIDAS Civil NX, and then transferring it into the MIDAS FEA NX. And then from there, Rajesh N will talk you through the modeling approach, including how the geometry, the deterioration, the prestress and the meshing were represented. And then we'll move on to the results, focusing on load paths and stress distributions. And after that, we'll run through the verification and validation checks that we undertook to ensure that the model was behaving realistically. And this was really important because it allowed us to determine how the results can be trusted and give us confidence in the model. And then we'll discuss how the 3D model was then used to inform the repair strategy. So with that in mind, I'll now move us on to the project itself and discuss a little bit about the history. So the structure dates back to the 1960s, and it's a free-span post-tension concrete bridge. It incorporates half-joint details at each end which support adjacent drop-in spans, and the bridge carries a single carriageway of traffic. So with regards to the history, so the structure underwent a routine principal inspection as part of the client's normal maintenance strategy. And it was through this inspection that significant durability issues were identified, particularly at the half joints and more specifically at the nib. The half joints were found to be in poor condition, and these inspections identified several defects, including delamination, spalling, cracking, concrete section loss, water ingress, corrosion and section loss of the reinforcement, or primarily affecting the soffit of both half joints. So as a result, the inspection highlighted the need for an assessment, and this is where WSP came into the picture. WSP was subsequently contracted to undertake a strut-and-tie analysis of the half joints in accordance with CS454, CS455, and CS466, the structural assessment of concrete half joint and deck structures. So the assessment explicitly accounted for the deteriorated concrete identified during the principal inspection. And when this deterioration was taken into account, the half joints were found to be overstressed under the 40-ton ALL Model 1. And this ultimately led to the conclusion that the half joints were unsafe in their current condition. So the client subsequently instructed WSP to carry out the detailed design of the repairs to the half joints with the aim of reinstating the concrete condition and restoring it to the required structural capacity. So fundamentally, this meant that the deterioration identified during the principal inspection needed to be addressed through a targeted repair strategy focused on the damaged areas of the half joints. And as a result, the problem wasn't just about checking the structure in its final repaired state, it was about understanding how it behaved during the repair process itself. So to carry out the repairs, the areas of the deteriorated concrete around the half joint needed to be broken out. And in some cases, this was about 50 mil of material being removed in places. And then at the same time, the structure was going to be jacked to allow the bearings to be replaced. So the combined effects of section loss and jacking means that the load path through the half joint was going to be altered. And then because of this, what we needed wasn't just a detailed stress results, but a clear understanding of how the load path evolves as the repair progresses. So the key question that we needed to answer was, what level of deteriorated concrete can be safely removed during the repair without compromising the load path through the half joint, and particularly while the structure is in its temporary altered state during the jacking and bearing replacement, so that ultimately the structure can be restored to the required capacity. So for anyone less familiar with this type of detail, a half joint is effectively a local discontinuity used to support an adjacent suspended span. As shown in the diagram on the right, the half joint provides a seating arrangement that allows the spans to connect and transfer load between them. So this kind of makes the construction efficient, as the drop-in spans can be lifted into place and supported at the joint. However, structurally, a half joint introduces a sudden change in geometry, and as a result, a change in how forces flow through the section. So instead of forces flowing relatively smoothly as they would in a regular beam, they're forced to deviate through a much more localized load path. And this typically involves compression struts, tension ties, and concentrated nodal zones around the bearing region. And it's this disruption to the force flow that leads to stress concentrations and makes the detail far more sensitive to deterioration and damage. So having looked at what a half joint is, it's worth understanding why these details are often vulnerable in service. And as we all know, water is the enemy of any structure. And in the case of half joints, this is particularly important, as they are often located directly beneath deck joints or drainage paths. So this allows the water, often carrying chlorides and other contaminants, to leak through the joint and reach the reinforcement. And then over time, this promotes corrosion, leading to cracking, spalling, and the progressive loss of section as identified within the principal inspection carried out. And then at the same time, the reinforcement in these regions is typically congested and access is often limited, making both inspection and repair more difficult. And as a result, the deterioration is rarely uniform, and it tends to develop locally, right where the structural demand is at its highest. And that's why the engineering challenge isn't just about the overall capacity, it was about understanding the local load path and how much intervention can be carried out without compromising it. So while the half joints can be structurally efficient, there are also often highly sensitive details, and they often become the critical location when assessing and repairing these types of structures. So with that, I'll now hand you over to my colleague, who will go into more detail on how the half joints were modelled and discuss the key conditions and the deterioration drivers.
Thank you, Luke. Good day, all. Thank you for making it to the webinar. I'll take it from here. In a deteriorated half joint, as discussed earlier, the stress field is highly nonlinear. The geometry directly influences the force path. and the relevant actions are three-dimensional. This means conventional beam assessments or assumptions are weakened. The correct engineering lens is D-region behavior interpreted through Strut-and-Tie principles, and where needed, it should be supported by refined FE analysis. In D regions, the Bernoulli assumptions does not hold. Sectional stress blocks become secondary, and equilibrium is carried through local struts, ties, and bearing zones and nodal regions. STM guidances treat such regions as cases where conventional sectional methods are insufficient, and the load path must be idealized explicitly through a Strut-and-Tie system. But recent reviews likewise describe STM as a powerful but simplified lower bound method for reinforced concrete discontinuity regions, especially deep beams and similar short shear spans. As Luke described earlier, the repair project was initiated after repeated inspections identified deterioration concentrated at the soffit of the half joints. So the inspection history indicated durability issues driven by leakage at deck joints and subsequent chloride ingress. The deterioration itself followed a pattern we often see in older details of this kind. Leakage through joints leads to water ingress. Water ingress brings chlorides. Chlorides drive reinforcement corrosion, and this corrosion causes cracking, deformation, and therefore concrete loss. What makes this case more serious is not only that deterioration exists, but that it is concentrated at the nibs of it, which is one of the most structurally sensitive locations in this detail. So the issue is not just material degradation in a general sense. It is degradation occurring exactly where the load path is already demanding. Moving on. The governing condition for this study was the repair stage, not the normal in-service traffic. So during the repair, the suspended spans are supported externally. They are lifted off and the live load is excluded. The half joint is assessed under a temporary configuration dominated by self-weight, superimposed permanent effects, and the prestress itself. This changes the internal force route materially. So the question was not what is the normal traffic capacity of the bridge? It was how does the half joint behave when the structure is partially unloaded and some concrete is deliberately removed for repairs or during the repairs. Now, about why conventional assessment was not enough. The technical assessment framework or the TAF originally framed the half joint assessment using Strut-and-Tie concepts, and that remained the correct conceptual starting point. However, for the bridges repair stage questions, STM alone was not enough. First, the actual bridge detail included anchorage blocks, prestressing tendons, a full bridge width, variable restraints, and local deterioration patterns that are difficult to collapse into a single planar truss without losing important behavior aspects. Second, the repair condition itself was non-standard. The suspended spans are lifted and supported, the traffic is excluded, and the lower nib is checked under a temporary configuration dominated by self-weight, superimposed permanent actions, and prestressing. And the third is that the practical engineering question was location specific. Whether a concrete breakout of 50 mm or in localized cases up to 100 mm could be tolerated by the structure without disrupting the load path during repairs. Now, why we adopted a 3D FEA? A refined 3D FEA model addressed these issues highlighted earlier very directly. Rather than imposing a single Strut-and-Tie mechanism from the outset, it allowed the stress field to emerge from the actual geometry, the support condition, the tenon layout, and the stage deterioration. This simply did not replace STM, but it strengthened it. In modern practice, The most defensible route for a detail such as deteriorated half joint is often FE assisted STM. The FE model is used to visualize principal stress trajectories, identify the active load path, separate local singularities from disturbed regions, and stress regions, disturbed stress regions, and confirm whether a chosen STM is mechanically credible. Recent half joint research explicitly uses detailed finite element models as a benchmark to evaluate STM conservatism and to study uncertainty. While recent analytical works on existing half joints with distributed reinforcement highlights the value of FE models in identifying which bars and ties are actually mobilized in resisting mechanism. So considering this, we deliberately shifted from a force-based approach to a behavior-based approach. The intent was not to extract a single governing force result, but to understand how the half joint actually carries the load and where stresses concentrate. So this 3D FEA was well suited here because it could represent the true geometry, including section losses, and could explicitly incorporate prestress, which was fundamental to segmental box girder behavior. It also allowed us to distinguish between local hotspots that were expected in D regions and global behavior that governs the bridge stability and load transfer. Moving on. Before moving into the modeling approach, it is useful to briefly step back and explain what FE or finite element analysis is doing, particularly for those who might not use it regularly. At its core, FEA divides a structure into a large number of small elements connected at nodes. The governing equations of equilibrium and compatibility are solved at each node. And from the resulting displacement at these nodes, we derive strains and stresses throughout the structure. So unlike traditional beam analysis, which gives us force and moments at sections, FEA gives us continuous stress field across the geometry. That distinction was important for this problem. In a half joint, which behaved as a D region, the load path was not very obvious at the start. Forces do not follow simple linear distributions. Instead, they flowed through compression struts, tension ties, and localized stress fields influenced by geometry and detailing. What FEA allowed us to do was to visualize that flow of stresses. Through principal stress plots, we could identify compression trajectories, tension zones, and shear transfer mechanisms. Now, that doesn't mean that FEA replaced engineering judgment. It was quite the opposite. The results still needed to be interpreted using sound engineering principles to distinguish between meaningful stress patterns and numerical artifacts. So in this project, FEA was not used as a black box to extract a number. It was used as a tool to reveal how the structure actually behaved so that we could make informed decisions about repair limits. The analysis itself was structured around 5 questions. What condition we were assessing? How should deterioration be represented? What model extent is needed for realistic restraint? How should prestress and reinforcement be included? And what level of mesh refinement is needed at the critical zones? That gave a disciplined framework rather than just building a detailed model and hoping the output will be useful. This slide signals engineering rigor by showing that the FEA wasn't ad hoc. Every decision, whether it is boundary condition, material loss depth, or mesh density, was purposeful. We considered 2 deterioration scenarios: 50 mm baseline deterioration as 100 mm as a worst case scenario that bracketed the uncertainty in actual concrete loss. And the repair stage assumptions, that is, the spans were supported and no traffic was allowed or stated upfront, anchoring the results to a specific real-world condition. And the explicit modeling of tendons with 25 to 35% loss shows the analysis accounts for long-term pre-stress degradation and not just nominal design values. And we have chosen FEA, but why did we choose MIDAS to assist us in the FEA analysis? MIDAS FEA NX was selected because the analysis problem required a true 3D structural model with solid concrete, discrete or embedded 1D reinforcement representation, local support flexibility, an extractable solid stress field, and practical post-processing of principal stress directions. The official MIDAS documentation showed that FEA NX supported structural properties for solids, trusses, embedded beams, point springs, and elastic links as well. So it provided explicit solid stress result components, including principal stresses and maximum shear, and could display principal stress vectors on solid elements. Those capabilities matched the core needs of the half joint study, which was geometry-led behavior, embedded steel modeling, support idealization, and direct interpretation of continuum stress flow. So MIDAS FENS ticked all the boxes, and adding to it, we had a familiar workflow. That is, we were familiar with MIDAS Civil NX, so it ensured fast iteration and reduced modeling risks. And this slide shows the practical workflow. The geometry was transferred from a bridge and model environment, that is the MIDAS Civil. Reinforcement was brought in from drafting information, that is AutoCAD 3D. Tendon data was defined explicitly through spreadsheet entries. Overlapping of modeling certificates were cleaned, boundary conditions was assigned, and the model was then meshed and loaded within FENX itself. The point here is not the software sequence itself, but the modeling route allowed the as-built detail and repair stage scenario to be represented with reasonable fidelity, as we will see in slides to come. So the flow is, once the material properties were defined in FENX, the 3D solid model was itself imported from Civil NX. The reinforcement again was imported as a DXF file. The tendon coordinates were input into Excel and then imported into profiles within FENX. Then the geometry was cleaned, if there were overlapping solids within FENX, they were cleaned. And then the boundary conditions were assigned. The meshes were tested and refined. Then the solid phases were loaded as applicable. Then it was analyzed and we carried out a verification, some verification exercises. Then after the model was verified for as built condition, when we were satisfied with the behavior of the model, the deteriorations were modeled in. They were again verified against the initial as built model, and in doing this, we could establish a clear breakout limits. This slide demonstrates the interoperability between MIDAS Civil NX. What you are seeing is MIDAS Civil. This was a key efficiency driver in this project. We developed the structural base model in Civil NX, where the team is already comfortable with geometry definition, staging, and global behavior. From there, the model or even selected regions like the half joint, could be exported as an MCS file and directly imported. This MCS file could be directly imported into FENX, either as a pre-meshed or as a clean geometry. What this enabled is a very practical workflow. As a level 1 global analysis can be quickly transitioned into a level 2 refined 3D assessment without rebuilding the model from scratch in FENX. Once imported, the geometry could be mirrored or extended to create a full 3D representation. It was followed by a targeted cleanup where there were overlaps, as you can see in the screen now. The key point is not just speed, but consistency. We are refining the same structural model rather than creating parallel models with different assumptions in both civil and FENX. This significantly reduced modeling risks and improved traceability in an assessment environment. Furthermore, the frame model could be used as a baseline verification tool. We will see that in a later stage. Just going back, the modeling itself took us 2 hours in MIDAS Civil NX environment, and from there onwards, importing it into MIDAS FEA NX was just a matter of minutes. It took us quarter of an hour. And once the model was imported into FEA NX, the first task was to ensure geometric integrity. This slide shows the cleanup process, particularly the removal of overlapping or duplicate solid volumes that typically arise when converting a frame-based model into a solid representation. If not addressed, these overlaps could distort stiffnesses and could produce misleading stress results. So FEA NX provides a set of geometry editing tools, much like CAD, like trim, extrude, explode. These commands are, comparable with conventional CAD platforms and work in the same principle. These also allowed a rapid refinement of the imported model. We also organized elements into geometry sets at this stage that became important later as it allows selective assignment of mesh density, material properties, or boundary conditions. So this stage is not just housekeeping. It was critical to ensure that the model behaved physically correctly before any analysis was undertaken. And this process overall, it took us about an hour in FEA NX, considering the complexity of this model. This could have been a lot faster if the model was simple enough, like regular bridges. This slide focuses on reinforcement modeling, which is often a bottleneck in any FEA models. But here within FEA NX, it was handled very efficiently. The reinforcement geometry was imported directly from AutoCAD 3D as a 3D line work. Different bar diameters were grouped into different geometry sets, which allowed us to assign appropriate cross-sectional areas and properties during meshing. A useful capability here is selective simplification. For example, where corrosion was expected, the reinforcement groups could be assigned reduced effective areas to simulate section loss without explicitly modeling corrosion mechanisms. The key advantage was the fidelity without excessive modeling effect. We were not idealizing reinforcement as smeared properties. We were embedding it explicitly within the concrete, which improves how load transfer and stress redistribution are captured, particularly near anchorage and nip regions. Next is the tendon modeling. Prestress is central to the behavior of this structure, and this slide reflects how we modeled it explicitly. The tendon profiles were defined using coordinates data prepared in Excel and then imported into FEA NX. This allowed accurate representation of tendon geometry, including curvature and anchorage locations. Pre-stress forces were applied directly along the profiles with sensitivity checks carried out for losses in the range of around 25 to 35% as established in TAF. That range reflects a realistic long-term conditions for a structure of this age. This was in 60s bridge. The key point here is that the pre-stress is not a secondary effect. It defines the stress field in the half joint region. Particularly near the anchorage zones, it governs the compression trajectories and influences how loads are transferred through the nib. So modeling the tendons explicitly was essential to ensure that the resulting stress fields and therefore the interpretation of safe breakout limits was physically meaningful. The tendon modeling within Excel, it took us that is data entry. What we had was archive drawings which were not very legible, so it took us an hour to enter the coordinates of the tendons within Excel, and then in FEA NX, it was just the defining of the tendon properties, importing them. It just took us 15 minutes. So Next, the platform also suited to FE-assisted detailing studies because the same environment could combine solid elements for the concrete body, embedded truss type members for reinforcement, or line-like elements for tendon modeling, and point springs or elastic links to assign support flexibility where it needed to be introduced. MIDAS documents also note non-linear elastic functions for truss and embedded truss elements and for point springs and elastic links, which becomes relevant if a project later wishes to idealize steel softening, uplifted supports, or uplift only supports, um, or non-linear support stiffness, etc. For the scope of this assessment, the documented SAR model remained a linear elastic overall. But the platform selection reserved a route to more advanced refinement if that becomes necessary at a later stage. Further practical advantage is that the MIDAS team has published examples comparing tendon simulations in 1D, 2D, and 3D element environments, including FE NX solid models with tendons. So that itself was not a proof of correctness, but it did show that the vendor's workflow anticipates prestressing studies in solid FE context rather than only conventional beam models. For a prestressed half joint where anchorage zone effects matter, this was really important. Then the model scope and boundary conditions. Rather than modeling the nib in isolation, we included the central span and the half joint region so that the stiffness compatibility and load distributions were realistic. This reduces the risk that artificial boundary conditions drive unrealistic local stresses. To validate the support conditions and global behavior, we compared reactions and deflection strengths against an independent line beam model and our FENX model. The goal was agreement at the global level before interpreting local stress potents. If you can see the diagrams, the deflection pattern and the magnitude varied exactly. I mean, matched exactly. Next, the mesh strategy. The mesh was deliberately graded. It was coarse away from the half joint to keep runtimes manageable, and it was refined locally at closer to nib and anchorages where stress gradients were expected to be high. The refinement again focused on the nib, the re-entrant corners and anchorage regions where the stress concentrations were expected. We also carried out mesh sensitivity checks to confirm that the stress patterns and peak locations were stable within two adjacent refinements. This ensured that we were interpreting structural behavior rather than numerical artifacts. This level of refinement ensured that the stress gradients were captured accurately in critical zones while keeping the model efficient elsewhere to analyze. This slide illustrates meshing process and more importantly how mesh quality could be controlled. The mesh density again was not fixed. We iterated it based on engineering needs. Critical regions such as very critical regions were assigned finer meshes while less critical regions remained coarse for efficiency. Geometrical sets again played a key role here, which allowed us to assign different mesh controls to different parts of the model. If you can see here, the nib is the half joint is meshed separately. So this was possible to select different geometry sets and assign different mesh densities. To ensure reliability, we carried out convergence checks as stated earlier. The criterion we adopted was that the stress variation between successive mesh refinements should be within approximately 10% of stress variation. Once that threshold was achieved, we consider the stresses or the results to be stable. This step was essential because without convergence checks, there is a risk that the stress peaks are just numbers rather than reflecting structural behavior, actual structural behavior. Next is a very crucial part. Before interpreting any stress results, we first needed to confirm that the model was behaving like a structure. We checked global equilibrium by comparing applied loads with reactions. We benchmarked the boundary conditions and overall deformation profile against a simplified line beam model or a grillage model. We also verified that the compression trajectories and shear transfer were consistent with expected Strut-and-Tie behavior. Finally, the mesh sensitivity confirmed that the stress patterns were stable and not just random numbers. Only after these checks did we proceed to interpret the results. This slide is a key validation step. What you are looking at here is our principal stress plots extracted from a section through the anchorage region. The maximum principal stress highlights the tensile field, while the minimum stress shows the compression trajectories. Even though the structure is inherently three-dimensional, this sectional view allows us to interpret the load model or load path a bit clearly. The important observation is that the compression field forms a continuous and a coherent trajectory from the deck region through the half joint region and into the support. This is critical because it aligns with what we would expect from a rational strut-and-tie mechanism. The structure is effectively developing a compression strut and that transfer load through the disturbed region or the D region rather than relying on beam type behavior. On the tensile strut shown as dots, the principal tension fields indicate where cracking is likely to occur. These regions correlate well with the observed deterioration, particularly at the soffit and reentrant corners. This increases confidence that the model is capturing real behavior. So though the force flow is 3D and has multiple loading points, this resembles, it doesn't match, but resemble published literature. The key message is this: we are not forcing a load path into the model. The model itself is revealing it. And since that revealed behavior is consistent with established structural mechanics, we can rely on it to inform engineering decisions, such as defining safe breakout limits during repair. Now that we have established, we have made a sense check. For a D region, the most useful outputs are stress fields rather than just member forces. So the principal compressive stresses help visualize compression struts and confirm whether the load path is continuous and logical. The principal tensile stresses indicate likely cracking regions and can be compared with observed damage locations. Shear stresses, on the other hand, help interpret how forces transfer through the nib and around discontinuities. This stress-based reading aligns with behavior-based assessment and supports engineering judgment alongside code-based checks. How we use the stresses in bridge assessment? The half joint and corbels we verified with maximum shear and principal tension at reentrant corners, which was again cross-checked with Strut-and-Tie methods as per EC2 and CS466 corbel rules. In the anchorage zones, we used principal tension fields to size bursting and splitting reinforcement, and we compared the provided transverse reinforcements against the stresses to ensure its capacity. And we reviewed P3 increase, the compressive stress increase behind the anchor blocks, and P1 hotspots are deviators combined with stage losses to verify the pre-stress effects. We limited the tensile stresses for crack control, deflection, and serviceability to form solid displacement at control points. This formed a survey check. Now we have verified and the base model, that is the as-built model, and it was deemed acceptable. So we iterated this model to define the breakout limits. This slide shows how deterioration was represented in the model, and this was a critical modeling decision. Instead of reducing capacity through factors or condition factors or modifying material properties, we treated deterioration as an actual geometric loss of concrete. In practical terms, that means physically removing the material from the model, typically around 50 mm, not around, exactly 50 mm at the soffit as a baseline, and up to 100 mm locally for worst case scenarios away from the anchorage zones. The advantage of this approach is that it directly captures how the load path adapts to this reduction or to these missing materials. In a region, D region like half joint, behavior is governed by geometry and force flow. So if you remove material, you are not just reducing the capacity, you are actually altering the entire stress trajectory. So by modeling deterioration explicitly, we were able to observe how compression strut shift, how shear transfer redistributes, and whether the continuity of the load path is maintained or not. That insight is what underpinned the breakout limits. We were not relying on conservative assumptions. We were observing how far material can be removed before the structure itself began to degrade in real life condition through this model. Okay, this is where the analysis transitions into engineering decisions. Under the repair stage loading, the half joint behavior remained predominantly compression driven, which was favorable. The compression strut mechanism remained intact even with baseline deterioration, indicating that the fundamental load path is robust. However, the critical finding is that the location governs acceptability, not just the extent of damage. The deterioration near anchorage zones had a disproportionate impact because the regions are already carrying high local stresses, and it facilitated force transfer from prestressing. So based on this, we defined a controlled repair strategy rather than a single global limit. We allowed breakout depths in the range of 50 to 100 mm where it was found to be acceptable, as and where it was found to be acceptable. But with tighter restriction in and around anchorage zones, equally important is the construction condition. During the repair, the half joint must be relied upon structurally. So full temporary support was required so that the load path is controlled externally while intervention takes place. So the outcome is not just a capacity check, it was a location specific intervention envelope grounded through observed structural behavior. This allowed safe repair without introducing unnecessary conservatism or over restrictions. The key findings. The primary outcome was a confirmation of a continuous compression load path from the deck region to the support through the half joint, which was consistent with strut-and-tie behavior. Stress concentrations were present at anchorage zones and geometric corners, which is expected for this type of detail. The key is that they remained localized. The tensile stress zones align with observed soffit and corner cracking, but under the repair stage configuration, they were not governing. Sensitivity checks showed that the load path remained intact even with increased prestress loss and of course decreased prestress loss and greater deterioration, indicating a robust overall behavior for the intervention scenario. Now, this slide brings together the analysis outputs and translate them into engineering decisions. On the right-hand side, you can see the temporary support arrangements used during the repair stage. This reflects the actual condition under which the half joint was assessed with the suspended span lifted and load paths altered. On the left, the stress controls at the soffit were used to define allowable breakout zones. They are not arbitrary. They are derived from how the stress field redistribute when the material is removed. The upper section shows the cuts through the anchorage region. This was critical because it demonstrates why stricter limits are required near anchorages. The stress concentrations here are significantly higher, and any loss of material has a disproportionate effect on confinement of concrete, which is unacceptable when viewing it in terms of higher compressive stresses. So the output is not just visualization, it's a location specific repair envelope. It links stress behavior directly to the practical intervention rules, which was ultimately what the project required. While we discussed the project, it is also important to be clear about what this model did not do. Concrete was treated as an elastic linear framework for the purpose of stress interpretation. We did not simulate full nonlinear cracking or bound slip or corrosion expansion or even collapse progression explicitly. Instead, the model was used to study mechanism, load path continuity, stress concentration, and repair sensitivity. That is entirely appropriate for the intervention question being asked, but it is important not to climb more than what the model was built to answer. Speaking about the limitation, if further refinement is required in the future, this model provides a solid base for far more advanced analysis. For example, non-linear material models could be introduced to explicitly capture cracking, crushing, or undetention softening in the concrete. The bone slip behavior between reinforcement and concrete could also be modeled, where anchorage performance is critical. Time-dependent effects such as creep, shrinkage, and pre-stress relaxation could be incorporated if long-term behavior becomes relevant. In addition, stage construction or repair sequencing could be simulated more explicitly to track load distribution during intervention. So, apologies. For local detailing, anchorage zones could be refined further to study bursting and splitting stresses in more detail. It is also possible to simulate a progressive deterioration or a staged breakout to understand how the structure responds incrementally. So the current model is appropriate for the intervention decision, but it also provides a platform that can be extended if a higher level of detail is required or if it is requested by the client. As a retrospective reflection, the main takeaway is that the half joint behaves as D region. So assessment needs to focus on load paths and stress flows rather than just sectional forces. In this project, through 3D FEA, done through MIDAS FEA NX was used to guide decisions, specifically to understand the consequences of deterioration and to define safe repair actions. The value of the model came from translating analysis insight into practical limits and constraints that reduced risk during intervention. The work therefore supported safety while avoiding excessive conservatism. Thank you all. Now we are open for questions.